Iterative methods for solving equations. When the exact solution of an equation is impossible to find because the roots are real, infinite numbers, we apply iterative methods consisting of approximate solutions to more complex equations through repeating procedures. The term iteration means repeatedly carrying on a process. In iterative methods, we first make a plan and choose to calculate the root values to a certain degree of accuracy, for example, to the nearest integer, tenth, hundredth, etc., and then, we apply the procedure as many times as needed to isolate the possible solution to the desired order of accuracy. Let's get more in detail about these procedures. Change of sign method. Before explaining the change of sign method to solve equations that have real numbers as roots, let's consider an example consisting of a first-order equation with one variable, which as we know, has a fixed root. Let's consider the equation 3x minus 5 is equal to 7. Solving this equation yields, we have the following as shown on screen. This means that for x equals for the equation is true, i.e. its left part is equal to 0. Now, let's suppose we don't know the root of the equation but we are going to guess it by identifying the zone where this root may be present. Let's take x equals 1. For this value, we have the following as shown on screen. For x equals 2, we have the following as shown on screen. For x equals 3, we have the following as shown on screen. As you see, we are getting closer to 0. This means that we are approaching the root value, which is still bigger than 3. On the other hand, if x equals 6, we have the following as shown on screen. This means we are on the other side of the root, i.e. it is smaller than 6. For x equals 5, we have the following shown on screen. As 3 is closer to 0 than 6, this means x equals 5 is closer to the true root than x equals 6. Therefore, the solution must be searched in the numbers zone that contains values bigger than 3 and smaller than 5, i.e. somewhere around the value 4. We know that the root is 4, as we have solved this simple equation. This example is used only for illustration purpose of iterative methods. Again, taking x equals 3.9 yields, we have the following as shown on screen. And for x equals 4.1 we have the following shown on screen. We can continue this way with x equals 3.99 and x equals 4.01. They give minus 0.03 and 0.03 respectively. Therefore, it becomes more and more clear that the root of this equation is x equals 4. In first-order equations therefore, the root is at the point x equals minus b over a. For x less than minus b over a, the sign of the left part of the equation is negative, while for x greater than minus ba, it is positive. The sign table of first-order equations is shown in the following on screen. Obviously, in first-order equations with one variable, it is not necessary to apply any iterative methods, as it is easier to solve the equation. The utility of such methods is more evident in higher-order equations. Let's explain this point through an example. Example 1. Find one root of the equation 3x cubed minus 4x squared plus x minus 1 is equal to 0, at an accuracy of 1 decimal place, that is near to the number x equals 1. Solution 1. For x equals 1, we have the following shown on screen. For x equals 1.2, we have the following shown on screen. Since we are getting closer to 0, we continue increasing the value of x by small steps. Hence, for x equals 1.4, we have the following shown on screen. Given that the result is positive, this means that we have gone beyond the root. Therefore, the solution must be searched between x equals 1.2 and x equals 1.4. Hence, let's try x equals 1.3 and eventually see whether the result is closer to 0.576 or 0.392. Thus, for x equals 1.3, we have the following shown on screen. Hence, since 0.169 is closer to 0 than 0.596 and 0.392, we take this value, x equals 1.3, as the solution of the original equation if we want to stop at one decimal place. The iterative method used in the previous equations is known as the change of sign method for solving an equation. Thus, according to this method, we must look for the solutions, roots, where the expression contained in the left part of an equation is about to change the sign. The values of an equation's variables for which the corresponding expressions are exactly 0 represent the roots, solutions, of this equation. The closer to 0 the value of this expression is, the closer to the correct value of the variable is the number chosen to represent the variable in calculations. There are two change of sign methods we can use when solving an equation through iterative methods. Method 1, going through values in order until there is a change in sign. For example, in the equation, we have the following as shown on screen. We can start from x equals 0 to substitute the variable in the equation. We have the following as shown on screen. For x equals 1, we have the following as shown on screen. For x equals 2, we have the following as shown on screen. Thus, since there is a change in sign, it is certain that one of the roots of this equation is between 1 and 2. From the results obtained for the corresponding expression, it is clear that the root is much closer to 1 than 2, as 5 is much closer to 0 than 132. Hence, we may continue with other numbers to get closer to the solution. For example, we can try x equals 1.1. Thus, we have the following as shown on screen. Again, we continue to increase the accuracy of the result by taking x equals 1.2. We have the following as shown on screen. Hence, we were able to localize more in detail the position of the root. It is between 1.1 and 1.2, closer to 1.1. If we want to increase the accuracy further, we can take x equals 1.11, x equals 1.12, etc., unless we obtain again a new change in sign. Method 2, using the half interval division to localize the root. This means that after identifying an interval where is a change in sign, take half of that interval and make a new calculation. Then, we consider again the half interval where there is a change in sign and consider the half of this half, 1/4 of the original interval, and so on. This procedure is carried out until we obtain the desired level of accuracy. For example, in the equation we have the following as shown on screen. When starting from x equals 0, this yields, we have the following as shown on screen. For x equals 1, we have the following shown on screen. Since there is a change in sign, the root is between 0 and 1. Thus, we take half of this interval, x equals 0.5, and make the calculations again. We have the following shown on screen. Therefore, the solution is between x equals 0.5 and x equals 1, as the change in sign occurs in this interval. Hence, we take again the half value, i.e. x equals 0.75. Thus, we have the following shown on screen. Since we obtained again a negative value, the solution must be searched in the other half, i.e. between 0.75 and 1. Thus, for x equals 0.875, we have the following shown on screen. In this way, the root is between 0.75 and 0.875. Therefore, if we want to round the result in one decimal place, we write x equals 0.8. If we want to write the result in two decimal places, we must continue further the previous procedure until obtaining the desired result. Example 2. Use the iterative method of half intervals to find one root of the equation x to the power of 5 minus 2x minus 2 is equal to 0. Write the answer in one decimal place. Solution 2. At a first glance, it is clear that one of the possible the solution must be searched between x equals 1 and x equals 2. We have the following shown on screen. We have the following shown on screen. Hence, taking x equals 1.5 as half interval yields, we have the following shown on screen. Therefore, the root is less than 1.5 as the change in sign is between 1 and 1.5. Thus, taking the value x equals 1.25 for the half interval yields, we have the following shown on screen. This means the result must be searched between 1.25 and 1.5. Thus, for x equals 1.375, the middle point of 1.25 and 1.5, we obtain the following as shown on screen. Hence, the root is between 1.25 and 1.375. This means that when rounded to one decimal place, the result is x equals 1.3. That is all for lesson 9.4.1. To continue this tutorial, please watch 9.4.2, Applications of Iterative Methods. Thank you for watching. Make sure to like and subscribe to keep up to date with new videos. For more information, calculators, and tutorials, please visit www.icalculator.info.